you search the web for science and one variable at a time, you'll find many sites advocating for only changing one thing at a time in experiments. Some will even list this as a tenet of the scientific method. Personally, I think there are times to change one variable at a time, and times to change every variable at once. Here, we'll talk about why you might want to change all the variables at once. In later videos, we'll talk about how to do that effectively. If you've had any training in science, you've probably heard at some point that there are three kinds of variables. Independent variables are changed to look for effects. A dependent variable is the result of changing the independent variable. Controlled variables are kept constant to measure the result. In other words, independent variables are the cause in the experiment, and dependent variables are the effect. Everything else is controlled to try and draw this relation. When you don't know much about a new system that you're studying, changing one variable at a time is a good idea. It lets you see what is actually affecting the outcome of the experiment, identifying important variables and allowing you to disregard unimportant ones. It is certainly true that you should do some of this first to find out what variables are important. What usually isn't mentioned is that this is a terrible way to optimize and learn more about the system once you know the variables that affect it. Changing one variable at a time, once you know what variables are important, can miss important relationships between the variables that you can only realize by systematically adjusting multiple things at a time. In other words, sometimes what we think are independent variables are actually interdependent variables, so we need to figure out how they affect one another. Let's consider the yield for a reaction that is affected by only two variables, the concentration of one reactant and the temperature. For simplicity, let's say for whatever reason, changing other concentrations or any other conditions didn't make any difference in the yield. The goal is simple. Let's find the conditions with the two variables that give us the highest yield, and ideally, let's do it in as few experiments as possible. More importantly, let's do it in the least amount of time as possible, because generally speaking, that's the more precious commodity. We started exploring our reaction. The best conditions we found initially gave us a low but solid yield of 37%, which was at a concentration of 0.1 molar and a temperature of 25 degrees. We're starting at about room temperature, so let's see if the yield goes up as we increase the temperature. In the beginning, the only light in the darkness, if you will, is a small signpost that says 37%. So you decide to set up a new reaction at 38 degrees. From that, you learn that the yield increased to 51%. That's a step in the right direction. Increasing the temperature again to 50 degrees, you find that you get 55% yield, still improving. Going up to 63 degrees C, you find that the yield goes down. Increasing the temperature in real chemical systems can decrease the yield for a variety of reasons. For example, the product may be unstable or byproducts may be encouraged by higher temperatures. But you aren't sure if that result is real. Does the reaction really give a lower yield, or did I screw something up? Maybe I'll go one more step. Let's try 75 degrees C. This time you get a pitiful yield of 33%, and you're pretty sure higher temperatures are bad for the experiment. The best we got fiddling with temperature was 55% at 50 degrees C, so let's see what happens when we increase the concentration. We'll keep things at 50 degrees C and increase the concentration from 0.1 to 0.15. We find that the yield decreases slightly to 49%. Again, we don't have error bars, and 55% to 49% seems like a small change. Is that real, or did I do something wrong setting up the reaction? Has one of my reagents gone bad? Let's try 0.2 molar just to see what happens. You do that and find that you get 50% yield, essentially the same as 0.15 molar, and less than the 55% you get at lower concentration. You decide that 55% is a good optimum based on these results. You tell your boss you've optimized the reaction. It has a usable, modest yield of 55%, which you got from doing 7 experiments in succession. The problem is, if you knew the real relationship between temperature, concentration, and yield, your surface would look like this, where the red indicates higher yields and blue lower. There's a maximum in the top right that we didn't find because it looked like the yield might be going down slightly with increasing concentration and higher temperature based on where we started. In the 25 to 75 degree range and 0.1 to 0.3 molar range, the maximum yield is at about 0.3 molar and 70 degrees C. There is a higher max not far away from where we stopped. To try and find the best conditions using one variable at a time, we did 7 experiments in series. Since we don't know what experiments to do next until we know the result of the experiment before, that takes 7 times longer than one experiment. If the reaction time and analysis was done in a day, it took about 7 days. Using a response surface method, which is one way to map the entire surface above to find the optimum, we would ideally want to do 9 experiments. These would include a 2-variable factorial design, which in this case is 4 experiments that define the corners of the domain. As we map out the domain, instead of natural variables, temperature and concentration, we'll use scaled variables, which will help us to map the surface more uniformly, among other things. The center of the design will be at 0, 0, and the axes will go from -1 to +1. Then, to get the curvature of the surface, we would add at least one center point and axial points like this. From these data points, we can get a complete map and describe the surface mathematically. So we'll know about the 85% yield we can get at 7 degrees C and 0.3 molar. More importantly, we know all the experiments that need to be done to accomplish this at the beginning. If we know the range we want to explore, we can set up these 9 experiments in parallel. This might take longer than doing one experiment by itself. Let's say it takes twice as long to set up 9 reactions in parallel as opposed to one single reaction. Even so, if the reaction time is a day, the 1 variable at a time method would take 7 days to give you the suboptimal yield. The response surface method would take 2 days, and a little math, to get the optimal yield. In future videos, we'll talk about scaling parameters, full factorial designs, fractional factorial designs, and other parts of the response surface method. Here, we just wanted to say it's okay to go wild sometimes. Change all your variables at once. Science is supposed to be about exploration. Changing multiple variables at once can help you get a better feel for the landscape you're working on. Thanks for watching this introductory video on response surface methods. We make these videos for fun and as a way of giving back to the community. If you enjoy the video, please subscribe and give us a thumbs up. Really, the best way to support our channel is to watch more videos, and we have quite a few up at a variety of levels. Thanks for watching.